Ionic bonding. Describe the steps involved in the formation of an ionic bond. How are they held together? Well, you got to think about valence electrons. Cations always have, I'll put a C here for cation. Actually, let me change that. I'll put an M there for metal. So your metals always have 1, 2, or 3 valence electrons. These metals want to give away 1, 2, or 3 valence electrons. Meanwhile, the nonmetals, these guys want to gain 1, 2, or 3. So this guy wants 1. So if you have a metal giving away 1 electron, maybe it goes to that nonmetal. This loses an electron, becomes +1. This gains an electron, becomes -1. If you have a positive and a negative, they're attracted to each other and they bond. Same thing with these guys. It's just basically playing a matchup game for how many valence electrons you have and how many you need. So if you have 6, you need 2 more. So maybe these guys can go there, and this will gain 2, this will lose 2, and you're attracted to each other. Now sometimes the numbers don't work out super nicely. So let's say you have a nonmetal who has 5 valence electrons. It needs 3 more. And maybe you only have a metal that gives away 1. Well, that's not good enough. That's going to help get this guy closer to the octet, but it's not going to completely solve the problem. So this metal might find a friend. And lots of these guys all donate 1 electron. And then this guy gains its 3, 1 from each of these. This becomes -3. Each of these becomes +1 because they each lose 1. And then we have a 3-to-1 ratio. So maybe we write the formula like this. 3 to imaginary 1. You can put the 1 there if you want, but it's usually imaginary. So long story short, metals lose electrons, they become positive. Anions gain those electrons, become negative. You have a positive and a negative attracted to each other. That's an ionic bond. And we use that, the ratio there, to figure out the formulas. Now, if you see Roman numerals, you just have to remember Roman numerals are the charge on the metal. It's not how many are in the formula, it's the charge on the metal. You'll see that in a minute. And when you use parentheses, whenever you have a polyatomic ion and you're going to write a number on the right of it. If you're going to write a subscript, for instance, if I have hydroxide, if there's just 1 of them, I just write OH. But if there's going to be 2 hydroxides, if I'm going to put a 2 down there, I better put that in parentheses. If I have nitrate and there's just 1 of them, I leave it alone. But if there's going to be 3 of them, I put it in parentheses. So let's see how this works out. Now the first thing you have to be able to do is figure out the charges. Hopefully you know the relationship between the periodic table groups and the charges they each make. You also should know the difference between an element found on the periodic table and those polyatomic ions. Now you will get a list of the polyatomic ions on the exam, but you should be familiar with them by now. All right, so let's do the first one. We got sodium bonding with sulfur. Sodium makes a +1 charge. Sulfur makes a -2. So this is an example of something that does not work out nicely on a 1-to-1 ratio. Sodium says here, I've got 1 for you. Sulfur says, that's great, but I have 2 missing electrons. I need 2. So it tells sodium, go find a friend. Another sodium in the container also donates an electron, and that's how sulfur gets 2. So there's 2 sodiums, Na2, hooking up with 1 sulfur. So this is sodium sulfide. Normal sulfur right off the periodic table, so it's an "ide" ending. Now potassium hooks up with sulfate. That's different. Sulfate, because it ends in 8, should make you think it's a polyatomic. You just need to know sulfate is SO4 with a -2. Potassium's trying to give up 1. Sulfate says I need 2 so I could stay together. 1 potassium doesn't cut it, so we get another potassium to donate, and then we have again a 2-to-1 ratio. So K2 and then SO4. Notice no parentheses because there's only 1 sulfate. We don't need another sulfate here. So this is potassium sulfate. Now, here's aluminum hooking up with nitrogen right off the periodic table. Nitrogen's in group 5, so it has 5 valence. It needs 3 more. So 1 aluminum is very willing to give up 3 electrons. The nitrogen needs 3. It's a perfect match, so it's a 1-to-1 ratio. So it's just ALN. That's aluminum nitride. Nitride means it's right off the periodic table, regular old nitrogen. Aluminum with nitrate is a different story. Nitrate, and the only way you know this is if you look it up or memorize it, is NO3 negative 1. Nitrate is looking for 1 electron, but aluminum says, I've got 3 to give you. And nitrate says, but I can't take all 3. I just want 1. So aluminum says, we'll go find 2 more friends. And you each can take an electron. So 1 aluminum gives away 3 electrons, and you need 3 nitrates to take them all. So we've got 1 aluminum hooking up with 3 nitrates. Now, if I'm going to put a 3 after the nitrate, I need to put nitrate in parentheses. So Al and then NO3 with a 3 after it. And that's aluminum nitrate. Now, you could think, oops, I deleted it all, I guess. You could think of this as kind of logic like I was doing, showing you that this wants to give up 3 and this guy can only take 1. Or you could use the crisscross method. Take this 3, not the plus, just the 3, and put it there. Take this 1 and put it there. And that's how you end up with Al imaginary 1, NO3, and we're going to put a 3 after it. Over here, they're the same number. Don't write this. Don't write Al3, N3. If they're the same number, they're the same ratio, then you just leave it alone, and it's Al, N. 1-to-1 ratio. All right, so let's use crisscross method from here on out, and it'll go much faster. The 3 is going to go there. The 2 is going to go there. Fe2O3. This is iron. Now, because iron's one of those funny guys that makes more than 1 charge, we've got to use Roman numerals. The 3 is because iron makes a +3 charge, and then just regular old oxide. Calcium and the phosphorus. This one's trying to give up 2. This one needs 3. Not a match made in heaven, so we crisscross them. Ca gets the 3 from the phosphorus. The P gets the 2. Now this is just regular phosphorus, so it's phosphide ending. If it was phosphate, you would have PO4 here. Iron 3. I love it when I see Roman numerals. It tells me the charge. I don't even need to look at the periodic table. Carbon 8. I like polyatomic ions because I know them. I don't have to look at the periodic table. Take the 3, put it here. Take the 2, put it there. So it's Fe2 and then CO3, and I want to write a number after my polyatomic, so that means my polyatomic needs to go in parentheses. Iron 3 carbonate. Almost done here. Strontium's in group 2, so it gives up 2 electrons. Hydroxide is one of those polyatomics that ends in "ide." It's not on the periodic table. I know it ends in "ide." You just have to know it. Hydroxide, you're going to use this one a lot, so get this one stuck in your brain. Hydroxide makes a -1 charge, meaning it needs 1. Strontium's trying to give up 2. And hydroxide says, I can only take 1, but I'll go find a friend, and we'll each take 1. So there's going to be 2 hydroxides. If you wrote this, it would be wrong. Because this is saying there's 1 strontium, 1 oxygen, and 2 hydrogens. And that's not what we want to show. We want to show that 1 strontium is hooking up with 2 hydroxides. So you need to put hydroxide, the whole thing in parentheses, and then the 2. And this is sodium hydroxide. So this is wrong. Copper 2 phosphate, love Roman numerals, tells me the charge on copper. Phosphate, you need to know, PO4 -3. Again, not a match made in heaven. It's not a 1-to-1 ratio, so I got to crisscross. The 3 is going to go after the copper, so Cu3. I'm going to write phosphate, PO4, and how many of them? I need 2. I don't want 42 oxygens and 1 phosphorus. I want 2 sets of phosphate. So Cu3, PO4, 2. And that is it.